Copper Alliance for this opportunity to talk about rural electrification models and costs and the insights that we've derived from working with the Homer model for so long. The thing that strikes me the most about this entire field is that there are so many choices. In fact, too many choices. In addition to all the traditional technologies, there are a wide range of new technologies, mostly renewable, but also things like electric vehicles, new storage technologies, the whole field of smart grids, et cetera, and demand response is opening up all kinds of new opportunities, and that's great, except a confused mind says no. Everybody wants to know what's best, and unfortunately the answer is that it depends. Depends on your location, what the resources are in that location. It depends on what you need energy for, reliability and opportunities for load management, and the technology keeps changing. It keeps getting better, which is great, but prices are coming down, performance is getting better, but it means the answers keep changing. So that's where modeling is really important, but it's also kind of challenging because particularly solar and wind being variable resources, the load's variable as well, the chronology is really important. So that means you need quite a powerful tool that can step through an entire year. Solar and wind also need to be part of a hybrid system. They don't stand on their own. So they need to be integrated with a dispatchable resource, whether that's the grid or diesels or batteries or some combination of those. And you end up with lots of choices. Finally, most of these projects are relatively smaller projects, so they can't be developed the same way really large power projects are developed. We need a more efficient development process which requires simpler tools that more people can use and don't require the same resource commitment to use them. So that's kind of why we developed the Homer software. I'm going to talk about it just a little bit briefly before I get into the insights that we've derived. It's become the industry standard for looking at hybrid power systems, particularly microgrids, but any kind of hybrid system really. It looks at a variety of conventional resources. The default is diesel, but actually any fuel-fired generation, whether it's a fuel cell or various kinds of turbines, they can run off diesel fuel or heavy fuel oil or biogas, whatever. Wide range of renewable resources. Solar is the predominant one now. Wind used to be and it still is an important one, but we also look at hydro and biomass, et cetera. Wide range of storage technologies. I'll talk more about that as we go. That's where there's an awful lot of innovation happening. And load management is often overlooked, but it can be a really important, it is a really important part of a well-designed hybrid power system. So just a tiny bit of history. As Fernando mentioned, we started developing Homer in 1992, 93 in response to the Earth Summit in Rio. And it was an internal model at NREL for quite a while, but in 2009, we got the exclusive license to commercialize it, spun off Homer Energy as a private company, and that's what we're doing now. In that time, we've more than quadrupled the user base, and the pie chart on the left just shows how diverse our applications are. In fact, most of those users in Western Europe and the United States are looking, well, are analyzing projects that are all over the world as well. So just a little bit of background on how it works. At its core, you need to meet the load in every hour or every minute. You can run it at for every minute of the year as well. Most people don't. So you do that for an entire year, and you've simulated how a system operates. You know how much fuel you're going to use, when you're going to charge and discharge your batteries, how much you're going to wear them out, et cetera. You need to calculate the replacement costs, et cetera. Calculate the full life cycle or net present cost for one system. That's the simulation innermost loop, if you will. Do that for hundreds or thousands of different design choices and find the least cost solution. That's the optimization loop. The new version of Homer lets you optimize on actually any variable, but typically cost. So that tells you what's best for a particular scenario, but there's always a lot of uncertainty, and so we think sensitivity analysis is really important. You want to be able to do some analysis, get some answers, even before you have all of the data you might ever want. In fact, you probably never have all of the data you ever want, but it's important to know what data is important, what data really changes an answer, and that's the data that you should put more resources into improving. So analyses like this tend to operate in sort of an iterative manner where you do a conceptual analysis first, or pre-feasibility analysis. You're not trying to get precise answers, and then you go and get better data and refine your analysis. And so that's the way we typically run perform analyses. So we use Homer to bridge different worlds, and there's some really important different worlds here. We talk to renewable advocates who want us to go to 100% renewable, or the world to go to 100% renewables as quickly as possible. But we also talk to utility operators, and that kind of talk scares them to death, frankly. They're real old school, know how to keep diesels running, and these are two completely different cultures, frankly. We also talk to power engineers who are used to very sophisticated engineering models that look at transients and dynamic stability and harmonics, and there's a whole class of very sophisticated models to do just that. They don't really look at economics typically. And we also talk to financiers. The finance community uses spreadsheets. So they have their own models, completely different kinds of models, and there's this huge gap in between them, which is where Homer sits. We find that if you have one model that all these different groups can use, it actually forms a communication tool that can really help bridge this gap and get these very diverse types of people communicating, and you really need that to happen if you're going to get a project developed. So that's why we have flexible data requirements. As I mentioned before, I think analyzing these projects needs to go in sort of an iterative fashion where at first you use some rough inputs and get some rough answers to know that you're sort of in the right ballpark. And then you can go back and get measured data. Measured load data is really valuable if you can get it. The wind projects really need good wind data, and that's hard to get and can be costly. And so you can operate it at different levels, and you actually need to be able to do that. So, and again, we use Homer for all kinds of things. The most obvious one is designing systems. It gives you a lot of information on how the cost is broken down between components, when replacements have to happen, maintenance versus fuel versus capital costs, et cetera. People use it just to look at the resources, or just to, and also to evaluate how much better does the technology need to get. So that's sort of at the research end. At the policy end, I've got a graph I've got two graphs to illustrate the last two bullets. This one refers to carbon policy, where you find people talking about these two endpoints. Let's go 100% renewable. No, it's too expensive. We can't do anything. That's the debate. Seems to be the debate. And if you have a graph like this, you can really see that the people arguing for 100% renewable are kind of giving ammunition to the people who are saying it's all too expensive. Whereas there's this huge region in here where you can save a lot of carbon emissions at very, very low or even negative costs. This is where the debate should be, is where in the middle here is where we should be heading in the short term, rather than polarized debate about the endpoints. And I just wanted to show this graph, if I can get rid of this arrow here, just to show that we really do look at every hour of the year. You can see, well, I'll bring this back. You can see when the diesels come on here. You can see when the battery's discharging. That's the light blue line. The dark blue line is the load. Here's a very cloudy day. Here's a sunnier day where the solar can meet the entire load and even charge the batteries a little bit. It tells you when backup power is needed, how the battery's getting used, et cetera, et cetera. So to move on here, let's talk about rural electrification. And I like to break the choices down into two broad categories. Individual systems, where each home or building or application has its own system, and microgrids, where you supply power to a whole village or whatever, a set of more than one customer or application at a time. The individual systems have really taken off. They're simple. Solar lanterns are taking off quite dramatically around the world. Solar home systems are sort of larger versions of that, where the panel and the battery are separated. And actually, these can be quite large systems. There's no sort of limit to how large this could be if you wanted to power a micro-enterprise of some kind. These could be several kilowatts. And they might even have a backup generator themselves, at which point you're sort of blurring the line a little bit between these two. Microgrids, they've also been around for a long time. In the past, they were just diesels and typically only ran part-time. But now they come in all different sizes. The small ones can be 100% renewable, but the real potential, I believe, is in what I'm calling a fully integrated hybrid system, which has both batteries and a backup generator. So I like this graphic here to sort of describe the electrification ladder, if you will, or on the left you start with traditional kerosene and batteries. Nobody's really using, that's unelectrified, right? And then there's sort of two different paths you can take. In the past, the upper path was the main way, using diesels, but a small diesel plant will typically only provide part-time power. Or you can do this individual solar as full electrification like you'd have in the city. But there are two very, very different paths with very, very different requirements about tariff structures, requirements for administration and management, and power quality, and what you can do with the power. Part-time diesels and individual solar systems are just radically different ways to provide sort of an intermediate level of electrification. So let me talk about each one a little bit more. Diesels, of course, have very low capital costs, which is why they kind of proliferate. So there's diesels, all over the world. You see these diesels in various states of repair or disrepair, age, and they're easy to maintain, and they require quite a bit of maintenance. But the knowledge of how to maintain a diesel is quite widespread. The issue with them isn't their capital costs, it's their fuel costs. And in the past, that might not have been as big a problem, but in the last few years, it's become a huge burden, and that's the problem we're really trying to solve. The problem is compounded by the fact that, even a good, really efficient, well-maintained diesel is pretty efficient at full load, but very inefficient at part load. So if all you have is a diesel generator, you're going to size it for your peak loads. You're going to size it to be a little bigger than your peak loads, which means if you try to power your off-peak loads, you're running that diesel just very inefficiently. The fuel efficiency is horrible, but it's also bad for the diesel, and the maintenance, you're going to create maintenance problems as well. So without batteries, a diesel really can only, a single diesel like this, can only really supply power in the evening, which is great for watching TV, and that definitely has value, but it doesn't have the same kind of value that daytime power would have for economic development, productive uses, and income-generating activities. There's also, and this is sort of a subtle, but I think a very important point, if the power is only on for a few hours in the evening, energy efficiency is not that big an imperative. If you think about it, a light switch is sort of the most elementary energy efficiency technology you could have. But I've seen lots of villages powered with these part-time diesels where people don't even have light switches. When the diesel comes on, the lights come on, and when it's time to turn the lights off, you turn the diesel off, and that works fine. And unfortunately, I mean, you know, it doesn't sound like it should work fine, but it actually does. In truth, if you're running the diesel, you kind of want to keep it loaded, so you don't. So villages with a history of being powered by a part-time diesel do not have any kind of attitude or experience with energy efficiency. So this is a new concept for them. One, it's actually very important when you go to a solar systems because they're very different in this, and especially in this particular way. They tend to be really simple. They can be all DC, or they can have a small inverter. Totally DC ones are becoming more popular. I think that's a trend that's happening. The cost of these has just plummeted, and so this is they're a really increasing trend to go to these individual solar systems. What's interesting about them is they actually can provide 24-hour power. It's not like, if the baby wakes up in the middle of the night, you can turn on the lights and help them. So that's a big advantage over a part-time diesel. The disadvantage is the quantity of energy available is limited, and it does vary from day to day, assuming there's no backup generator, of course. So that's where people with these individual solar systems become tuned in quite quickly and quite immediately to energy efficiency. Because they're managing their own system, and it's sort of obvious if on a cloudy day they just don't have as much power in the evening as they did on a sunny day. And the biggest challenge with these systems is battery management. People tend to over discharge them. They should always have a charge controller, but they don't always have charge controllers and those charge controllers should prevent over discharging the batteries, which is really important, but also prevent overcharging the batteries as well. So the charge controller is a really important but often overlooked piece of this. And also, without a backup generator, it's pretty hard to equalize the battery. You have to not use your system for an evening, so the next day the solar can charge it up. And even with or without a backup generator, equalizing the battery requires throwing away quite a bit of energy, just because when you're equalizing them, they can't absorb much power. It's difficult to manage those batteries. So the batteries typically don't last very long in these applications. So that's sort of the drawback to them. So where we really focus are on these fully integrated hybrids. They provide 24-hour AC power, often better than the central grid. And the way they do that is they use the batteries for the off-peak loads, and they'll have a diesel generator for the peak loads, and they size the solar to find the economic sort of optimum of how to minimize the usage of the diesel. So frequently you can have a diesel generator and use it very, very little, but just that little bit that you do use it saves you enormously on both the size of the batteries bank and the cost, et cetera, but also on being able to manage that battery bank and equalize the cells, for example, and prevent the batteries from sitting at low states of charge, et cetera. So the diesels can be a very, very important part of a fully integrated hybrid, even if you don't use them very much. The drawback to these integrated hybrids is that they're more complicated, obviously. And so when you're talking about rural electrification, there may not be an institution in the village capable of, or with any history or experience managing systems like this. They're like a mini utility, so you have to have metering, you have to figure out the tariff structure, you have to agree on the tariff structure, you have to administer that, collect the payments. And that is a huge challenge it's not really a technical challenge so much, a little bit, but it's the biggest issue that needs to be addressed to make these mini grids or mini utilities work. A huge benefit, a huge improvement are these prepay meters. That without that, this becomes really difficult. People are used to the concept of prepay with their mobile phones, and it's sort of a new innovation, relatively new innovation, and I think it makes all the difference in the world as to whether this concept of a hybrid renewable microgrid can play a big role in rural electrification. And if it can, it really changes the whole concept of rural electrification away from diesels and grid extensions towards more sustainable local solutions. So let me talk about grid extension just a little bit. That's the default along with diesels, and people are still talking about extending the grid. Our experience in many, many places is that the central grid can't handle the customers that it already has. That's, of course, every country is different, so that's not perhaps universally true, but in many, many places, the existing grid, the existing utility, is forced to have rolling blackouts, doesn't have enough capacity to handle its existing customers, let alone running wires out to new customers who are going to be even less profitable to serve, frankly. What we do in Homer, though, is we can calculate what we call this break-even grid extension distance. So calculate what it would cost to meet a particular load, whether it's a village or whatever it is, what it would take to meet that load with a hybrid system, which obviously doesn't depend on where it's located, versus the grid extension, which depends pretty strongly on how far you are from the existing grid. So the yellow line here is the life cycle cost, or net present cost of meeting the load with a hybrid system, and the blue line is the cost of meeting it from a grid extension, which includes both the cost of the grid extension itself, maintaining it, dollars per year maintenance cost on the grid, which is not huge but important, and the cost of power on the grid. And so that's the blue line, and where they cross is what we call the break-even grid extension distance. So this is a relatively small load, but it's saying if it's more than 2.42, arrow here. If it's more than 2.42 kilometers from the existing grid, that's where these two lines cross, that's what we call the break-even grid extension distance. I'm seeing a lot of, I'm just noticing people complaining about the sound quality. Let me try something and see if this is better. Sound quality. I hope it is. I'm just going to move on, though. So when we talk about design trade-offs, there's a really big difference between small systems and large systems. And small systems tend to be more renewable, rely more on storage, and less on diesels. The larger systems tend to rely more on diesels and have a lower renewable penetration. So let me go into that in a little more detail. And there's nothing magic about these numbers. I hesitated to put numbers on here because I don't want to give the impression that these thresholds are hard and fast rules. But your very, very small systems can get by without a backup generator. That will require some flexibility in how people use use the energy. But in the really small systems, putting in a big battery bank and managing your loads is more manageable than in larger systems. There's this intermediate size here where, and I'm saying 1 to 100 kilowatts, but don't take those numbers too literally, where a single generator is really useful, but it's not going to get used very much. But when you get into the larger systems, they're actually probably an existing diesel generator. They may, when you get into the megawatt scale, they probably aren't running 24 hours a day. They probably have multiple generators. Hopefully, they are running those generators, the big ones for the peak loads and the smaller ones for the off-peak loads. That's not as common as you might hope, but that makes a huge difference. That's It's when we run Homer, that we often find the biggest savings comes from just managing your diesels more efficiently before you even start talking about renewables. Um, and in the past, in the larger systems, people tried to shy away from batteries altogether just because lead-acid batteries, they just don't last very long. They're maintenance hassle, and et cetera. That's changing rapidly. What people don't realize, though, is that batteries play multiple roles within a hybrid system. So the first thing you need is, if you've got a substantial amount of renewables on a small system, you need to make sure that system is stable, when clouds pass or winds gust and lulls and et cetera in the wind. And so for that role, you don't need very much storage. A minute is plenty just for stabilization purposes, and flywheels will work for that. As you add more renewables, you want to be able to turn the diesels off, because if you can't turn the diesels off, you are sort of limited in how much renewables the system can absorb, because they're pushing the diesels into operating less efficiently, and what you end up doing is curtailing the renewables to protect the diesels, unless you can turn them off. Because you don't want to run the diesels at very, very low loads, and you are going to need to ramp those diesels up quite rapidly when clouds pass. So spinning reserve is really important, and batteries can do a really good job of that. And if you have enough spinning reserve, you can actually just turn the diesels off, and you've got a buffer to get them back on again. So that requires maybe 15 minutes worth of storage. It might only take 2 minutes to get the diesel back online, but you need a buffer there. That's still not a lot of storage, actually, and it's mostly power instead of energy. When people think of storage, they usually think of it in terms of, well, let's take the what we call load shifting, I guess. Take the solar power that's created in the middle of the day and use it in the evening, which is often when the loads are highest. And that's really intuitive and logical, et cetera. But for that, you actually need a substantial amount. You need several hours worth of storage. And so that's a much more challenging application for the storage. Obviously, you can get to much higher renewable penetrations if you do that. But there's this intermediate application, which is, okay, during the evening peak hours, we're going to have to run the diesels, because we just don't have a battery bank big enough for that. But in the middle of the night, to keep the street lights on and keep refrigerators cold, et cetera, the loads are very low, we can turn the diesels off and run and use the batteries for the off-peak periods. So I just mentioned at least 4 different applications for batteries, and they're all different in terms of sizing that they require, costs, and appropriate renewable penetration, et cetera. So let me just show a few results that from Homer showing where PV is cost effective. And the 2 biggest uncertainties, the things that have changed the fastest, are fuel prices. Just bounce all over the place. They're very difficult to predict, which is along the x-axis. You may not be able to read the numbers, and I apologize for that, but we're going from $1.20 a liter at the far right to 20 cents a liter, which is kind of absurdly low at the left, but I wanted to have a broad range here to make the impact more visible. And on the vertical axis, we have PV capital costs in dollars per watt. So $1 a watt, which is unrealistically low at the bottom of the graph, and $8.50 a watt at the top. And this is just for the PV itself, not the inverter, not the batteries, just the PV, but total installed costs, including mounting hardware and shipping and installation, et cetera. So $8.50 a watt is pretty high. And what it shows is that for most of this, PV is very cost effective. If you've got extremely low diesel prices and extremely high PV prices, that's not true. But really, pretty much anywhere, PV is going to be cost effective at some level of penetration, which I'm not showing on this graph. And I intentionally picked a location, a solar resource in northern Canada, just to make the point that this is true pretty much everywhere. Excuse me. It's true pretty much everywhere. If it's true in northern Canada, it's true in Africa and India and pretty much everywhere else in the world. So the solar resource is not as critical as, say, the wind resource, which is very, very critical. So this is for a very small application. 45 kilowatt hours a day is sort of a tiny application. The next slide is the same resource, but a much larger application, so 2,000 kilowatt hours a day. And you can see the region where PV is not cost-effective has expanded because the diesels are more efficient and cost-effective as you get larger. But it's still, PV is still cost-effective pretty much everywhere. And again, this is northern Canada. So this is just to make the point that the advent of PV diesels as a truly cost-effective alternative for rural electrification is true pretty much everywhere. So just to show you how some of the economic outputs, we can do return on investment, comparing, obviously these renewable systems cost a lot more, so are you going to get a payback or a return on that investment? And here's a system we did. This happened to be in southern Africa, so the resource is better, but it has a 3.5-year payback or a 29% internal rate of return, which is excellent. And of course, you'd want to do this yourself for your own estimates of costs and loads, et cetera, but this is not atypical for the kinds of returns we see running Homer. And why is this? It's because diesel prices have gone up and PV prices have gone down. And diesel prices have been going down lately, and so that's a little worrisome, but actually PV prices are matching them. So the grid-connected renewable world has been talking about grid parity forever, and as the holy grail of when will we get to grid parity. But in the off-grid world, the diesel world or rural electrification world, that happened a few years ago, and even though diesel prices are coming down, PV prices are coming down just as quickly. Let me talk a little bit about this concept of penetration, because it's pretty confusing. People throw around these percentages of 30% renewable, 80% renewable, and it's very, very unclear what they're talking about. There's at least 6 different ways to measure renewable penetration. And without going into a lot of details, the highest number is going to be, well, on a weekend or sometime when loads are really low, but the sun's really shining in the middle of the day, or if it's a wind system in the middle of the night, but it's really windy, you've got 1 hour there out of the whole year where that's your peak instantaneous penetration. That's going to be your highest number. The same system with, say, a 25% peak instantaneous penetration on the wind, if you calculated the actual proportion of annual energy produced by that same system, it might only be 5%, and the fuel savings might only be 4%. Solar is the same idea, so there's a factor of 5 difference because it's daytime instead of night. The numbers aren't exactly the same, but it drives me kind of nuts, to be honest, when people throw around percentage renewables and they haven't defined what they mean by how they're defining percentage. So I tend to stay away from percentages for that reason, and talk more generally about renewable regimes, low, medium, and high penetration, and define it by the system architecture. So in a low penetration, you don't have to do anything. But this is very low penetrations, but if the variability introduced by the solar or wind is on the same order as the variability of the loads, the system can handle that. No special controls are required, but you're very limited in how much renewables you can do that way. At some point, the renewables are pushing that diesel down to its minimum load, and you need some way to curtail the renewables to protect the diesels. So SMA has a fuel saver controllers, but there's a lot of different ways to do that, and that's what they do. They don't change the way the diesel operates. They simply curtail the renewables to protect the diesels, and you can get more renewables that way. And it sounds inefficient because you're curtailing the renewables, but frankly, it's okay to curtail the renewables a little bit. But again, you're limiting how far you can go with that, because at some point it gets silly to install more renewables if you're just curtailing them. So the real value, you can really start to get a lot more renewables if you can turn off the diesels. And if you have a larger system with multiple diesels, maybe that means switching from the big one to the little one. But in order to do that, you need this buffer that we talked about earlier. And to run completely diesel off, you actually need a totally different kind of power inverter. There's a different, qualitatively different architecture and different power electronics required. So these are distinct regions, and the percentages at which you go from one region to another depends on all kinds of factors: the weather patterns, the load patterns, the layout of the grid, the inertia of the generators. It goes on and on. The reliability requirement, the tolerance for frequency and voltage deviations. So I don't like to really talk about this in terms of percentages, but these are very distinct architectures and power electronic requirements. So just to finish up on this little diatribe I'm giving you on penetration, but here's another very, very typical result from Homer. I think this is actually from Aruba, so it's a pretty large system, like 120 megawatts or so, and it has a really good wind resource, and it shows that you can put a lot of renewables on the system and at negative cost, reducing the cost of power. And you can see I've defined renewable penetration very conservatively here based on actual fuel savings. So, but at some point, to remove the last 20%, if you will, of fuel consumption, and replace that with storage, basically, with renewables and storage, gets very, very expensive. And this is the class. These curves all look a little bit different depending on where you are and the size of the system, and et cetera, but they all have this characteristic shape, which is you can accomplish a lot at little or no cost, or negative cost in this case, and then at some point it gets prohibitively difficult to get the last little bit of fuel consumption out of the system, unless you can be very aggressive about load management, which is a little impractical if you're talking about a whole country or a whole island the size of Aruba, but in small systems perhaps you can do that. So to wrap up a little bit here, what are the lessons that we've learned from working in remote power for decades here? And just a few things I think are kind of interesting. People think, oh, renewables, well, what are you going to do with the sunsets? Well, you'll do what you've always done. So that's not difficult. The challenge is, what do you do when you have too much power? And what we've learned with working in Alaska, where they have 26 wind diesel systems up and running, they also have a large need for heat there, is a secondary load where you dump, if you will, excess power into a thermal load. Is very controllable and improves the economics of the systems, and it's for displacing other fuel consumption. But it also, because it's very controllable, there are systems in Alaska that run 100% on wind without the diesel running at all, without batteries, just by controlling the amount of power going into these dump load. Heating is a particularly convenient dump load, but you can do similar things with water treatment, water pumping, desalination, ice making, chilling, cooling. Not quite as conveniently, a little more complex controls to do that, but the concept is the same. The other thing that is really important to think about is what to do when it stops too abruptly. That's the whole spinning reserve that we talked about. You do have to think about these ramp rate issues. And then storage is a huge topic. We should have a whole webinar just on storage. It's not just for load shifting, it's for stabilization, it's for spinning reserve, and in the past people kind of tried to shy away from it, but the technology is improving so rapidly that that's changing quickly. We think that these microgrids are the future. There's a lot of talk about smart grids, and I'm in Boulder, Colorado, which was supposed to be the first smart grid city in the world, and it really was kind of a fiasco. And there's a reason for that. Large utilities shouldn't be innovators. They can't be innovators. That's not their job. They have security obstacles. They have regulatory obstacles. Their job is to keep the lights on, and innovating on a power system the size of North America or Europe is like changing the tire on your car while you're still speeding down the freeway. But smaller systems can innovate, and not only can they innovate, but they kind of have to, because their dependence on oil or liquid fuels means they have sort of an economic imperative to get to renewables faster. Doesn't take a lot of renewables before you're at high penetrations, and you have to deal with these stability and load management issues, and it's already happening. So mentioning Alaska again, I've been to a really remote, isolated Eskimo village in Alaska, where they have a wireless network for the whole village, and the power to individual appliances, heaters, in the homes goes up and down in real time with the wind, stabilizing the grid through a wireless network. This is the real smart grid. It's actually happening in these remote places. And eventually that technology will be universal, but it's sort of interesting, I think, to see that in these remote places that have never been cutting edge before, and really don't have the technical and financial resources to do this on their own. But this is where this technology makes the most sense today. There's lots of different kinds of markets for these microgrids. The ones that we're focusing on today, I think, are the rural electrification. So I've made it red there, but I just want to point out the same technology is of great interest to the military. It's in the U.S. we're really gotten focused on resilience after the storms in the Northeast. Then there's some niches that are very interesting, like ecotourism, the mining industry, et cetera. It's the same technology in all of these markets, or similar. There's a lot of joint lessons to be learned. So finally, I'll wrap up so we can have some questions. There's lots of choices today. I think the challenge is not lack of choices, but too many choices, and sorting through them, figuring out what actually makes sense. That's where we hope to be helpful. That's what we designed the software to do. Doing nothing is the worst choice, because the status quo of just running diesel generators really isn't sustainable. There's stepping stones. I'm a big fan of these solar lanterns and solar home systems, is to get people started, but eventually people are going to want high quality power. That's where these fully integrated hybrids can come into play. In the that's going to take time. So I think this individual solar systems have a big role to play in the meantime. And I can't, like I say, a whole nother webinar just on what's happening with storage technologies now. And so I won't go into a lot of detail there, but it really does require careful analysis, because there's so many different ways in which storage can be used, and it is a big piece of the total cost of these systems. So I want to thank you all for listening, and hopefully there's some questions. I'd be happy to answer.